So if you look at this sheet, anytime I give you a sheet that is colored like this, I want you to keep it. It's a reference, and it's potentially a reference that will be important all semester, and for those of you taking BC, all year. Okay? So don't throw this away. Keep this in your binder even after this unit. Okay? Go ahead and take this and flip it over on the back. All right. Hey guys, our goal is to limit the number of problems you have to do at home without help. So we're going to be mostly quiet so we can get this written down, okay? So, to be differentiable, if derivative is a noun, differentiate is a verb. So the derivative is the thing that you find, differentiating is the process you do to find it. Does that make sense? Differentiate is how you find a derivative. So the math that you guys were just doing, your result was called a derivative, but the process you were doing was called differentiating. Okay? So to be able to differentiate something, to be differentiable at a point, and we're going to call the point A, means that f prime of A exists. So if I can find the derivative at A, that means that the derivative at A has to exist. This is your duh statement. Okay? Like, duh, if I can find the derivative, clearly it exists. Does that make sense?
Yeah.
That's what that's saying. So you know that you're differentiable at a point if that derivative exists at that point. Okay? All right. To be differentiable on an interval, and our interval is going to be A, B. So that's an open interval. I'm not including the endpoints. I'm saying everything in between the endpoints. So to be differentiable on A, B means that the function is differentiable at every point on AB. So this would be like I would say the polynomial function is differentiable on negative infinity to positive infinity. That means I can find the instantaneous rate of change at every single point on the entire curve. I always can find that slope at every single point on the entire curve. Instantaneous rate of change, right? Because the derivative just means the slope at that individual point. Mm-hmm. Yep. Yep. Okay. It can be found. Yep. That's what it means to be differentiable.
So, with the rate of change, when we use like the f of x minus f of a over whatever.
Mm-hmm. So I'm using all these words interchangeably. Instantaneous rate of change, slope at a point, derivative, they all mean the same thing.
What's the slope at a point when you find?
That's the instantaneous rate of change. That's the slope at that single point.
Okay.
Mm-hmm. All right. And then last, we're going to say that differentiability, your ability to be differentiated, differentiability, that is a really long word. So your ability to be differentiated comes from yeah, the limit definition. So your differentiability, the ability for us to find the derivative or the instantaneous rate of change at a specific point, comes from limits. And that's because what we just did is we spent half the period finding a derivative by using a limit process. Okay? So this is what I was talking about yesterday when I said the limit as x approaches a from the left of the derivative has to equal the limit as x approaches a from the right. So this is what I was saying for this unit, how the limit of a slope equals a slope. And for us to be able to find the derivative at a point, the left side slope and the right side slope have to be the same for us to conclude that there is a derivative there. Okay? So if you flip over this pink sheet, you're going to see the different places where we cannot find derivatives. Okay? So go ahead and flip over your sheet once you're done writing. Can I flip? So here, if you guys look, this is called a corner. It comes together at a corner. If you look at 0, the left side slope looks like a -1, and the right side slope looks like a +1, and -1 and +1 are not the same. So here we would say that the reason you cannot differentiate this at 0 is because the left-hand limit and the right-hand limit don't agree. I'm not talking about the limit of the function. I'm talking about the limit of the derivative. So the limit, the left-hand slope and the right-hand slope do not agree with each other. They're different. Do you guys see that? Okay, so the slopes aren't the same. So if you're trying to find the slope right here, our left-hand slope is -1, our right-hand slope is +1. That's not the same, okay? This one is called a cusp. So cusp and corner, sharp turn, all of those are essentially the same thing. Again, we have the same issue at 0. The left side slope is negative, the right side slope is positive. Those two slopes do not agree with each other. Does that make sense? Okay, so if we were to be doing this using the limit definition of the derivative, we would find that the left-hand limit and the right-hand limit were not the same. Okay? If we look at this one, the reason that this one does not have a slope is because we would have a straight line right there. Our tangent line is a straight line, so that's a vertical line. What is the slope of a vertical line? It's rise over run. Oh, rise over run. That's how we find slope, right? It doesn't run.
1 over 0.
Yeah, so it could be like 1 over 0 or 5 over 0. So you can't find the derivative at a part of a curve where it looks like it has a vertical tangent line because that slope is undefined right there.
So is it undefined or 0?
No, it's not 0, it is undefined. So the slope of a vertical tangent line is undefined. Okay? So we would say our derivative is undefined. So we can't find the derivative right there. Here, we can't find the derivative not because the left-hand limit and the right-hand limit don't agree with each other, because in this case, you can see that the slope on the left side and the slope on the right side are both 0. So in this case, the left-hand limit and the right-hand limit don't agree with each other. This time, we can't find the derivative because the graph is not continuous. So if your graph is discontinuous at a point, you cannot find the slope there. Yes?
Later on, we have this find.
Yes, we are studying that in this unit. Okay? And then if something, other weirdness, there's a bunch of different things that could happen, but again, in an oscillating graph, we can't find the instantaneous rate of change because it's oscillating. Okay? All right, go ahead and flip your paper back to the back. We're going to add one more thing to the back side of this pink sheet, and this is super, super, super important, so write it big, underline it, star it, whatever you need to do. This is a theorem. And the theorem states, if a function f of x is differentiable at a, dang it, or differentiable at x equals a, then f of x is continuous at a. So that's the theorem. If f of x is differentiable at a, then f of x is continuous at a. And there's a contrapositive to this, which is kind of like the flip side. And this contrapositive is very important. if f of x is not continuous, at x equals a, then f of x is not differentiable at x equals a. So what this tells us is there's an important relationship between a function being continuous and it being differentiable. So we can't assume that just because it's continuous means it is differentiable, because if you look at the front side of your sheet, these two graphs right here, well, all three of these are all continuous, but they're not differentiable at 0. So it doesn't mean if it's continuous, it is differentiable. But the flip of that is true. If it is not continuous, it is definitely not differentiable. And that is an idea that we'll use repeatedly throughout the year, just saying first, it's not continuous, therefore I can't find this derivative. That's an important conclusion to be able to find. It's also important to know if you can find the derivative somewhere, then the graph is continuous there. So that is important to know as well.